Swayam Prabha. Digital India. Educated India.
So moving on to the exercise. So again, the solution book is available. You can directly click on this to open it in Colab. Those who are not able to, so let me first try here. So even on Colab, there is some issue with torch geometric. So first of all, check if you are able to run this first thing correctly. So this will first install this torch geometric libraries and its dependencies that are required. So if any error occurs, this would turn to red, and then you will not be able to run this notebook in the Colab. So for those who are not able to run this in Colab, you can download the py or the Python file, and that you can run in the native Python, you can say native Python exe. So for that also you can install directly using pip install torch geometric and all this. So this would get installed easily. So yeah, we are able to run this. So once this is installed, so for this particular example, we are using Cora dataset. So Cora is just a citation network database dataset that is available. So this is not a dataset, because why we didn't went with an example of 3D model. It is time consuming and it is difficult to present in such a short lab session where we have to train as well, and we want to evaluate and show as well the data, how we are training and how the model is evaluated. So for that, it's difficult to use 3D dataset directly currently. So we are using this example. This is well-known example. So just for understanding sake, you can just have a look. So for this dataset, it's actually a citation like citations of different research papers based on neural networks, machine learnings, deep learning, and based on that they have created a graph basically. So first we'll go ahead with our custom GCN layer implementation. So here we will use this particular technique where we calculate the degree matrix. We use the adjacency matrix to calculate this. So this is basically a constant value. And this is the function signal. You can say the feature vector of the previous layer, you can say. And these are the weight parameters that will be trained basically. So you remember in the previous exercise, we manually set the weight of the linear layer as identity matrix. So we don't want to do that. We want to train our network to find these values. And this is the non-linear activation function, which will then give the output of the current layer, you can say L+1 layer. So going on to the GCN layer. So message passing is you can say a module in PyTorch geometry where you need to implement the again forward method and the message method. So this is basically again derivation of the torch NN module, but this is more optimized for this geometric deep learning things or graph neural network architectures. So we want to basically add one linear layer. This is linear transformation layer. So again, this is the exam, you can say solution file. There is a exercise file as well, where you need to do fill these to-do layers. So whoever is interested can work on the exercise file and then maybe see the solution. But as I guess we have got less time, I will just run over to the solution file only. So as already mentioned, so for graph convolution layers, we have to add a self connection. So for that, what we do, PyTorch geometric has a helper function add self connection, or you can say add self loop. This will basically add self loops to the data. And once that is done, we then call this linear layer that is there, and we linearly project those particular feature vectors. So we calculate the degree matrix. So for that as well, PyTorch has got a helper function degree. This will calculate the degree matrix of the graph. We then, so it's raised to -1/2. So that has been taken care using the power function. And this is just the normalizing term. So you remember 1 by under root the degree I degree j term. So that is there. And we do the propagation of this, and this is the normalization term. So what actually message will do is message will consider the jth node. So for example, you are going from I to j. So for that, the jth node, so in this graph from 1 to 2, so xj would be this the second node basically. So once we have created this GCN layer, we'll create a network. So this is again torch and end module. So this is the forward propagation module we implement. And here we implement our GCN layer that we have implemented here. And the output of the first layer is 16. So as this is 16, the input of the second layer would be 16. Output would be number of classes that are there. So this is just the initialization of the layers, and the actual implementation is done in the forward method. So here we call the first graph convolution. Then we apply nonlinear ReLU activation. So dropout is again another term where we, so we will be learning machine learning, will have a better idea. We randomly ignore some things, some nodes while training. So that is there. And this is the convolution, another layer. And at the last, we have the softmax layer to get the single output basically. Or you can calculate the probability, normalized probability. So this was our graph convolution network. So now PyTorch has got, PyTorch geometric has got its own GCN conv layers. So internally it has implemented the GCN convolution from the paper, similar to what we have. And we will use that for this GCN network PyTorch model. So here, instead of our GCN layer, we are using GCN conv. And normalization you can do as true cast, up to you, true or false. Depending upon this, there would be slight performance difference. And in the forward layer, basically it's the same thing that we have done for our network, but the main difference is here we are using pre-implemented layer of convolution, and in the previous one we are using our own custom implementation. Once that is done, what we will do, this is just a helper function to plot the graph. So this is the training method, which will be used for both networks basically, where we pass in the model and the optimizer and the data that we want to train on. So it is same thing as already discussed in the previous lab. We just do optimizer, then we do backward propagation and we step. And once that is done, we calculate the training, or you can say validation accuracy and testing accuracy. And we'll print those accuracies and for in the graph form. So yeah. And in the testing method, it is again similar. We are calculating the between number of correct predicted data and false predicted data. Based on that, we generate the accuracy values. Okay, so now this is the main thing. So up till now, what we have done is model layer construction and everything. So now what we do, we want to load the Cora data set that is available in PyTorch geometry. So in the data set, there is a plantoid uh, function which has got such type of data sets of you can say citation data set, Cora, Mutang, enzymes, etc. So you can load it. So you can provide a path where it will be downloaded temporary. If it is available already at this location, it will not download and it will directly use that data set at that point. So you can just plot this data set, and this is just the device. So for ours, it could be CPU for now. So you can see this has been downloaded from the where it has been hosted. And once that is done, we will plot a graph of the data set. Okay. So this is there. So you can maybe if you work in a Python environment, you'll be better able to zoom it a little bit. But it's okay. So these are nodes basically are the research papers, and the links are basically the citation they have done. So those will have edges in between them, and uh, the colors basically represent different classes of paper. For example, neural network, deep learning, etc. So once that is done, what we will do is we will create our own GCN network that we have created, and we will also create and we will just pass the data set to it for training, and we'll just cache the training and testing accuracies for our data set. So we have done for 100 epochs. So loss is 0.05, training accuracy is 1, testing accuracy is around 0.78. So around 78, 79% testing accuracy we have achieved. And this is with our custom convolution implementation. Now, if we go ahead with the PyTorch implementation, okay, so we have also trained the pre-implemented PyTorch GCN implementation, and it's the same thing. We have just passed in the same data set to that pre-implemented layer and trained the model. We have also cached his test accuracy and training accuracy. So same, we have ran the training for 100 epochs. The loss is slightly better than ours, 0.035. Accuracy is 1, and the testing accuracy is also slightly better than ours. It is around 79.3, so around 80% accurate with the pre-implemented CCN layer. Now you can plot this training and validation accuracies of both the models. So this blue one is the custom GCN train accuracy. So the blue one is our training accuracy, and the orange one is the validation accuracy. So this is our accuracy, slightly lower than what pre-implemented GCN accuracy we have. Yeah, so this was a brief example or lab session for implementing our own GCN layer and comparing it with the pre-implemented GCN layers. So any questions related to this? So with anyone, any questions? So here we have used the plantoid, or you can say Cora dataset. But the same thing, if you want to work on a 3D dataset, then you will have to think how that 3D dataset would be consumed. So even I am personally researching, or you can say working on a project, my personal project, where I use point data for classification and using the graph convolution layer, means based on the graph neural network. So current PointNet implementation is different, and this what I'm working on is also different. So the scope is huge. There is a lot of things to research currently, and yeah. Any questions anyone has? So after this, I will just show you one quick a demo of my work. Actually, it's still work in progress, but I will just run the inference for you to for an example. But once everyone is done with the lab, you let me know. Has everyone completed with the lab 3? Okay, okay. That should continue. You let me know once you have done. Also, these labs are available at GitHub, so anyone who later on requires it can download it or work from that. So it's no hurry to understand everything just right now. Okay. Yeah. So this is one of my personal work that I'm trying out currently for points classification. For now, I have used the ModelNet 10 dataset that is available. So it has got 10 categories of mesh data available, but I work on points for now. So I have trained a model based on GCN and PointNet, both you can say. And currently I'm able to get accuracy of around 85 to 80%, but still it is work in progress. It's not completed. So what I will do is I will just take a random mesh from this the data set. So the data set basically has got two sections. One is train section and another is test section. So this training data was already used by me for training my model, but the testing data was not used. So for classification, I can use any of this randomly. So maybe you can, I will just try if that works or not. So maybe you can suggest which section, which class I should try for point classification. Anyone can suggest anything from this for now. Anyone? Okay. Okay, so Darshil says SOFA. So I will go for SOFA and the test data set. So randomly, I will just uh, select any file for classification if it works or not. So I will use this mesh file. So first, it will show us a mesh view of this particular file. And based on that, we'll use that data for inference, basically. So I have got CUDA installed on my system. So it basically uses for the first time, it takes a little time to get started. And yes, I haven't used PyTorch. I've used TensorFlow and Keras. So are you able to see this SOFA mesh, or you can say SOFA model? So we'll try and see if we are able to classify it correctly or not. Okay, so it has misclassified it as a dresser. So that didn't work well. So maybe we'll try some another model and check if we are getting correct result for that or not. So we'll go to some another model, maybe chair is to say, just randomly select.
Using mesh-based neural networks, right? Or point.
Yeah, so I'm using mesh to generate point data basically, and then add some noise during training. So
Okay, it's
these
point.
are basically public available data set, so it's easily available for prototype purpose.
Right, ModelNet is quite popular.
Correct,
I'm just
correct.
asking, your network is working on uh, individual, it's basically working on point cloud or mesh?
Mine on points.
Oh,
Okay, we are able to classify this as a chair correctly. Okay, so maybe one more we can try some another category, maybe monitor. Let's see if we are able to classify this or not. So this is just a use case that I'm trying out. So as we are not able to provide lab for such session, so I thought it would be useful if you can see actual application that is running based on what we have learned today. And so that would be helpful for you all instead of just, so this is a monitor. Now let's see if we are able to classify it or not. Oh, we are classifying it as a nightstand. So yes, as I mentioned, currently the accuracy is around 80 to 85%. I don't remember exactly, but training it more would make it more robust and will increase the accuracy. So this has been trained for just 100 epochs, you can say. So if I train it for some more epochs, then maybe the accuracy would increase in a better way compared to what it is right now. So yes, any question anyone has related to this, or any feedback related to the session that has been conducted would be good enough for me. So what should we, is the session helpful to you, and how did you like the session? So this is also misclassified. So you see the resemblance between this table and the monitor. So in the monitor, the previously which we ran, it has also had similar shape basically. So such type of example are very helpful to identify if our model is working correctly or not. So at this point of time, this is still in work in progress. And so probably there's much improvement required for the prototype as well. So yeah, all of you just unmute and just let me know feedback regarding the session. And the test files, or you can say the lab section files, would be available on the GitHub, so you can just refer it afterwards as well.
So, sir, in this project that we are giving a mesh, means of file, right? And
Yeah, you can get an STL file as well to this, but the ModelNet dataset we have got only off file, so I'm just using it for currently demonstrating you.
okay, and internally it is creating interrelationship between points, or we can say
Correct,
right. Okay,
correct.
and then based on these all points properties, it will classify mo- this object. Let's say it's a monitor or chair.
Correct, correct. Yes, true. So the point data set is not easily or freely available on which we can train our model. So this is the best way where we can use the mesh data set that is extensively available and very popular, and use it for our purpose.
Final questions from the participants? Comments? Zabit, this is from show.
Yeah, do let me know your feedback, participants. That would be helpful for us. This is correctly classified. So actual input to our model is this particular thing.
Right.
Yeah, it's not the
Point cloud.
mesh.
Right.
Yes, correct. And we also do add some noise to the actual mesh so that we can generalize the model.
To avoid overfitting.
Sorry,
Avoid overfitting.
avoid what? I'm not able to get.
Overfitting.
Yes, correct. Yeah, because if the model data are very clean, then they could not generalize to the actual data that is available.
Right.
Noise is required.